good morning, good afternoon, depending on your time zone. So, hello everyone and welcome. Thanks for joining to this UXL Foundation Language SIG meeting. I'm Biagio Cosenza. Today is a very special session because we are celebrating 20 years of trading building blocks. We have a great hour ahead because we have a talk from Michael Voss from Intel, which is current oneTBB architect, and he will talk about the evolution of TBB from what it was from the first release to today and what is planned ahead. And then we also have two meetings, what I call the community talk. We are experimenting something new. We are trying to pick people who are actually using the project to come here and to say how do they use it. So today we will have two short live stream meetings. One is from Kylie Knoepfel from Fermilab, and another one is from Federico Ficarelli from CINECA. So we also have a little bit from all around the world. And I stop here. I leave. I let Mike to start, and please go ahead.
Okay, I think, yeah. Hopefully you can all see did that work? No. Hopefully you can see my screen, yes?
Yes.
And I want to point out, I see on the call as well, we have Arch Robinson, who was the original TBB architect joining today, and then Dave Polson, the original manager of the TBB team. So welcome to them. They'll remember at least the beginning parts. So today, what I'm going to be doing is basically presenting a little timeline beginning in 2006 through this year, 2026, and just talking about the important moments when features were added, the evolution of TBB over time, and eventually get to its role in UXL and oneAPI ecosystem today. There's a lot of content, so I welcome questions, but maybe at the end so that I can get through everything. So the story really starts prior to 2006. So around 2004, Herb Sutter published his essay, The Free Lunch is Over, which warned developers that the age of ever increasing clock frequencies was ending and that performance would be achievable through multi-core and multi-threading, and that mainstream hardware vendors were all moving towards multi-core and multi-threading. And it's true that parallelism was around in HPC long before this time, but mainstream computing was different. So unlike HPC, mainstream computing was on multi-program systems. More than one thing could be going on at a time. You didn't have batch systems where you were getting exclusive access to the machine. The code bases were complicated and modular. They were using third-party libraries. In HPC, you had a lot of monolithic C and Fortran. Mainstream was, a lot of C++. So there was this real fear in the industry that mainstream developers would struggle to use multi-core and multi-threading. And also fear that the years of legacy mainstream serial applications would not be ported quickly enough for people to want to upgrade. And I remember at this time being in a workshop where people actually were getting their first multi-core laptops and they were commenting how they couldn't tell a difference in the performance from their last laptop to the new one. And so this was a real fear in the industry. Why, would people even be interested in getting multi-core? So on July 26, 2006, Intel released its first mainstream multi-core processor, the Intel Core 2 Duo. And 1 month later, on August 29th, TBB 1.0 was released, initially as a closed source library. And there were some really important decisions that were made as part of that first release. First, it was going to be a C++ library-only solution. And this was done so that people could adopt it quickly. They wouldn't have to wait for it to propagate into their specific compilers or change to a new compiler. And it also meant that it could adapt quickly because there was no uh, body that was steering it at that point, and it was didn't need to roll out into compilers. And it was also there was a focus on some key components. So there would be high-level generic parallel algorithms as a C++ template library, and these mostly targeted data parallelism. And these algorithms weren't specific math or domain-specific algorithms. They were parallel patterns like parallel loops, reductions, scans, pipelines, the key things that you needed to implement parallelism in software. It also came with concurrent containers, a map, a vector, and a queue, a scalable memory allocator, since that could be a bottleneck in parallel applications, and then some helpful utilities like atomics, mutexes, and timers. Another key decision at that point was that the implementation of the threading was actually going to be on top of a work stealing task scheduler and not people wouldn't be programming directly to threads. And this was inspired primarily by the Silk programming language. And there were good properties, and that's why work stealing and tasks were chosen. One is that it could react to system load and load imbalances, which was key for mainstream platforms because, again, like I said, these were complicated, multi-programmed platforms. And also at the time, we were marketing this as a future-proof way to do parallelism because we were asking people to port their applications and they could over-decompose their applications into tasks, which were very lightweight. And then as the core counts increased, which we expected they wouldn't have to go back and revisit their code. As more cores were added, the scheduler would just be able to spread those tasks that they over decompose their problem into across the ever increasing number of cores. It also allowed composability because you were using lightweight tasks, you could expose parallelism everywhere. And that would be in the application and third-party libraries, and they'd all be scheduled by this single shared work stealing task scheduler. The other key choice was that it was prepared to be open source. It wasn't open sourced initially, but there was already thinking along those lines. So this, for those who are unfamiliar with TBB, this is just an example. I think this example has been around in one form or another since 2006. It's a Mandelbrot computation, which is interesting for work stealing because each point in the Mandelbrot's in the complex plane is computed independently, so it's embarrassingly parallel, but the amount of work varies significantly. So it's helpful to be able to steal tasks when worker threads become idle. On the bottom left, you can see the serial implementation is just a doubly nested loop that calls this function mandel. And on the right, you can see an example of what TBB looks like. Here's a generic function. You pass in a range and a body, and at each point in the range, the body's applied. Now, in 2006, there were no lambda expressions. So this example here that's shown is actually a little bit simpler than what it would look like in 2006, where you'd have to write your own functor or function object. But this is the flavor of what TBB is like. So right out of the gate, TBB was pretty successful. And 1 year later, after its initial release, it was open sourced. And it was announced at OSCON 2006 or 2007, the O'Reilly open source convention. And customers wanted it to be open sourced. They weren't sure about, moving to a vendor specific solution. So open sourcing relieved that. And Intel was so interested in making multi-core programming successful that it was the path that Intel was willing to take, even though this was very new for the company. And there was a lot of angst about giving away software to everyone, including competitors, for free. But it was successful right out of the gate. It won awards that year. James Reinders published his book, Intel Threading Building Blocks. And O'Reilly assigns an animal. You don't actually get to choose your animal. So there's always an animal on the cover. And some are like no-brainers, like Python gets Python. But for TBB, they assigned a wild canary. And so at the time, I remember marketing being concerned about this, like what are we going to do with this bird? But they told the team and the marketing team itself, embrace the bird, and we did, and it's been our mascot ever since. We Intel actually didn't own the copyright to the bird that was drawn on the cover, so this cartoon bird that was drawn within Intel was became our mascot. An interesting note is that in 2007, TBB was open source. It was also the year that CUDA was first released. So a big year for parallel programming models, 2007. The first couple years after this, TBB started out very pure uh, with a small set of algorithms, a random work stealing scheduler, but it was being adopted quickly, and we started getting requests from customers who were using it in real applications, and we had to make pragmatic choices. So we added things like a thread. So our tasking library added TBB thread, which acted as a transition towards what eventually became C++11's stood thread. A task scheduler observer, which allowed customers to do things like pin the worker threads to particular cores, which we wouldn't have initially thought would be a good idea. Thread local storage, and to work in real applications, cancellation and exception handling. And as an open source project, even though initiated by Intel, we were open to contributions and we were getting new OSs contributed and ports to additional non-Intel processors like PowerPC and the IBM Cell processor. And it was taking off in certain industries. Autodesk Maya adopted TBB as its threading layer, and you can see a quote on the right where they talked about that. So now a few years into this, in 2010, we were starting to see other options emerging. One one that we were uh, collaborating with was actually Microsoft's Parallel Patterns library, which was similar to TBB, um, and it worked with the Windows concurrency runtime. And so we were wondering, like, is the time of TBB coming to an end? Other options are going to appear. We decided to make TBB compatible with PPL and the concurrency runtime, working with Microsoft. We added this resource management library, RML, so that TBB could better compose with the concurrency runtime as well as OpenMP. Initially, we were targeting mainstream computing, but we saw it being used as well in HPC by people who liked C++. And we included additional functionality over time, including, uh, again, compromises. We initially were data parallel work stealing. We added enqueued tasks, which executed out of a global FIFO queue and were for fire and forget kinds of work. We added task priorities to what used to be just random work stealing. And from PPL, we got task group, which was a simplified tasking API. So moving ahead yet another year, in 2011, we were starting to see a lot of customers use cases that had graph-like structures in them for execution. And so we added the flow graph, which allowed people to express data flow and dependency graphs directly in TBB that would then execute on top of TBB tasks and the work stealing scheduler. And 2011 was a big year for C++. The C++11 standard was approved. It included lambda expressions, which made using libraries like TBB so much easier because you could pass in your body just as an argument as a lambda expression. Again, useful for parallel programming. They standardized the memory model so we could think about it more easily. There were a lot of fundamental things around threading added, like stood thread, mutex, atomic, condition variables. And this is a point to just remember, TBB predated C++11. So prior to this point, and even at this point, TBB, to port to a new platform, you had to implement all these things that needed to be done in a platform-specific way. There was no standard way to get an atomic, for example. So TBB was being quite successful. Um, there was in 2014, there was multi-threading for visual effects. A book was published that included a chapter of how TBB was being used in the VFX industry. TBB was included in the inaugural VFX reference platform, which was the list of tools that the Linux VFX community agreed to use so that all of their tools and plugins would be compatible with each other. And TBB was selected as the CPU tasking threading backend. And again, as I mentioned a bit earlier, even though we were targeting mainstream computing, we saw that people who liked C++ were choosing TBB even in HPC applications. So CERN and ITEP published parallelization of particle transport using TBB, as the high energy physics community was embracing TBB. And applications and platforms continued to become more increasingly complicated. So transactional memory was appearing, and we added some support for that because applications were and libraries were embracing parallelism everywhere. We had a task arena that allowed people to isolate different kinds of parallel work from other kinds. We were being embraced across finance as well. In 2015, TBB was used in an implementation of Stack A2, which is an industry benchmark for analytical workloads and pricing and risk. And it set a speed record. And this was at the time when Xeon Phi was around. And TBB was used both for the parallelism within the Xeon and Xeon Phi, but also a flow graph was used to coordinate the offload to the Xeon Phi. So skipping ahead a little bit to 2017, the C++17 standard was approved, which added parallel algorithms and execution policies. So again, we're thinking, okay, maybe parallelism is working its way into the standard. We're really starting at this time to think, what is TBB's long-term place in the ecosystem? Well, that same year, Intel released Parallel STL, which was an implementation of parallel algorithms and execution policies, and TBB was used as the threading backend for the CPU. The same year, TBB moved from being GPL2 to Apache 2 at the request of customers. And like I said, we're thinking about what is our place in the ecosystem. And GPUs were becoming increasingly popular. So we were trying to figure out, should we be executing on GPUs or what should we be doing? And one of the things we decided was we should definitely play well with offload to things. And one of the first features we added in that regard was a sync node to the flow graph, which would allow you to communicate with an asynchronous activity, such as offload to an accelerator. And then it could execute a callback that would restart a task when that work was finished. So the idea was to work alongside with accelerators, but TBB would stay primarily as a CPU-oriented library. Continuing this trend, we saw that other things were using TBB as a backend now for CPU. Initially, back in 2006, 2007, we were marketing ourselves as the high-level abstraction for adding parallelism. And of course, people were still using TBB directly, but it was also being used as a backend for other even higher level abstractions. So people who were calling libraries from Python, we added Python support and TBB for Pi, which allowed people who were using multi-threaded modules they were calling from Python to share the same TBB work stealing scheduler amongst those modules to have better composability. OpenVINO was first released that does AI inferencing, and it selected TBB as the threading backend. Um, and like I said, this was a trend that had been going on. TBB, for example, had been a backend option for Thrust even as early as 2012. The end of 2018, in December, at Intel Architecture Day, the oneAPI project was announced as a project that was about simplifying programming of diverse computing engines for across CPU, GPU, FPGA, AI, and other accelerators. So we were in the process of working on how we were going to be a part of that story. By 2019, TBB had acquired a lot of tuning hooks and advanced features. So the first book came out in 2007. TBB was a much smaller, pure library at that time. By 2019, we had task arenas, we had priorities, we had various ways you could control execution of the scheduler. You could still get good performance with very simple approaches to using TBB, but there were other ways that you could very take a lot of control over how TBB would execute. And so we decided we needed to update a book that included all of this additional performance tuning information, and that was Pro TBB, which was a very successful book. This year, Parallel STL, built on top of TBB, was being shipped as part of TBB by Intel. And oneAPI was starting to take shape, announced the previous year, with SYCL at its core for heterogeneous computing. We also continued to add things to TBB like concurrent associative containers. So 2020, the first release of oneAPI happens. And it was the DP C++ compiler, which is Data Parallel C++ compiler, and it supported SYCL. And SYCL is analogous to CUDA as a way to offload to accelerators, including CPUs. And in the implementation that shipped with that compiler, if you were offloading or running your kernels on a CPU, that would go through OpenCL, and OpenCL was implemented on top of TBB when using the CPU. So we were starting to see our role in this whole heterogeneous environment. This year is when we started to revamp TBB into what would become oneTBB. And at the end of this year, it was released as a beta. Parallel STL split from TBB and became part of oneAPI DP C++ library, oneDPL, which was also released as a beta that year. And it was 2020, C++20 was approved. It included things, smaller additions for parallelism, but included coroutines, JThread, barrier, latch, semaphore, stop token. To the TBB library, because systems were getting larger, core counts were getting larger, we were adding things like constraints for task arenas so you could execute on specific NUMA nodes. And I guess coroutines were in the air. We added resumable tasks that allowed you to be able to suspend a task that was executing and then have another thread or task resume it at some point in the future. oneTBB was the first, amazingly, because this is like 13 years in, this was the first major compatibility break for TBB. So prior to that, you could have compiled your application and you could just drop in a new TBB DLL or shared library and it would be compatible. But we decided in this transition to oneAPI that we were going to take this opportunity to reduce technical debt, embrace modern C++. You could still use TBB with just C++98 at that point. We didn't require C++11. And this increased portability. So we did. We embraced modern C++ requiring C++11 to use oneTBB. This meant we could remove things like TBB atomic in favor of stood atomic, both as a user-facing feature, but also in our own implementation, which allowed TBB to be more portable. Like it was ported to ARM, and that I believe was much easier because you didn't have to go through and implement all of those platform-specific things like atomics in order to port TBB. It just used stood atomic. We rethought some things like how initialization was done, how you could set global parameters to make it much easier to reason about. We removed our lowest level tasking API in favor of a simplified API. And we're still working with customers now to add additional features to our simplified API to capture all the use cases that they have. And we did a general overall code cleanup. So in 2021, the previous year, oneAPI was released, which was the compiler and SYCL. In 2021 came along toolkits, which included the compiler, but also tools and libraries that were compatible with SYCL. These included things like oneMKL, oneDAL, data analytics library, oneDNN, oneCCL, oneDPL. These were all part of the base toolkit and the HPC toolkit. And many of these libraries, when they were using SYCL, but when they executed on CPUs, either they directly use TBB, or if they most use TBB directly, but if they use SYCL, then SYCL itself would run using TBB as the threading backend. And that continued to be the case for customers who are directly expressing their applications in SYCL and targeting CPUs. So I think it's probably clear as I've been talking that what we wound up with as TBB's role in the oneAPI UXL heterogeneous computing ecosystem is captured here. On the left, you can see there's these four quadrants. On the left, there's things that are for CPUs. On the right, for accelerators. On the top, there are the libraries and abstractions for expressing the parallelism and launching work. And then on the bottom are the languages and libraries and models for expressing the actual kernels themselves. And TBB is squarely in that top left quadrant. It's about CPUs and it's about expressing the parallelism. And the reason why it's a good choice for that is for all the points I've mentioned already. Composability, work stealing allows it to adjust to load imbalances. It performs very well. So it's analogous in some ways to things like Level 0 or OpenCL, which would be used for launching work onto GPUs and other accelerators. In 2023, so earlier, the UXL Foundation was established. In 2023, TBB transitioned to be under the governance of the UXL Foundation. And in addition, things continue to become increasingly complicated in terms of hardware and applications. And so we were adding things like support for hybrid CPUs, E-core, P-core, low power E-core, big core, little core, those sorts of things. And also some of our existing customers wanted to take their applications and run them in web browsers. And so we added support for WebAssembly so they could still have their application parallelism expressed using TBB, but run within a browser. Getting very close to today now. We've been still working with customers on improving our tasking. We have a preview feature for dynamic task dependencies that is simplified relative to the lowest level API back in the 2007 time range, but very powerful. Because we moved to oneAPI and we embraced modern C++, we thought it was time to update the TBB book once again. And so in 2025, we released today's TBB that covers this revamped version of TBB. And the community and user base is still very strong. I just show here a snapshot from SteamDB. So Steam is the most common way people get download games for PCs. And you can see what's shown here is the number of individual game releases by year that somewhere in the package is included TBB. And this is both TBB and oneTBB. Um, and you can see, as of last year, we were seeing like over 3,500 individual game releases um, that year that use TBB either directly or indirectly. And we're on track this year to have a similar number. So this brings us to now. Um, so we are under the governance of UXL Foundation. So our repository is at GitHub UXL Foundation oneTBB. The way we are acting now, like our future, is really shaped by our community. So we provide milestones so you can see what's in our upcoming releases, including the features, improvements. We list the code cutoff dates and planned release dates for those releases. If you have suggestions for new features or want to report bugs, you can talk to us through GitHub issues. In 2007, we open sourced TBB as part of our move to the UXL Foundation. We're trying to embrace open design. And so whenever we're designing a new feature, we document the steps we're taking in the design. So under the RFC directory in our repo, you can see a number of folders, including a proposed folder. So through PRs, we will discuss new features and develop a proposal, and our community is completely welcome to participate in that. If it goes into a preview as an experimental feature, it moves to the experimental directory, where that experimental design is documented, as well as the exit criteria. What are we looking for in previewing this thing? What kind of questions are we trying to answer? And then if it becomes supported, then it moves to the supported directory, and that document acts as a design document to give people insight into what it's about, and so they can refer to it if they want to participate in modifying it in the future. So in 2026, ISO C++26 was also approved, which included the execution control library that started out many years ago as like executors, and now it's senders and receivers. And the reference implementation, which is mostly implemented by NVIDIA, includes a oneTBB backend. So TBB is still viewed by the community as like a very attractive way to express parallelism for CPUs. So just quickly, what we're working on within our team: performance, always performance. We made that future-proofing commitment many years ago, and we're still holding to that. We're always looking at new architectures that are coming out. Recent work has been around large core counts, the performance impacts of NUMA and hybrid architectures. As I said, we're improving our tasking APIs. Almost all our features are driven by customer requests or collaborations. So there's things going on around flow graph, support for C++20 modules so that you can use TBB as a module instead of including it. And we are working on improving composability through a recently open sourced, as part of the TBB repository, Thread Composability Manager, which helps improve composability, TBB, and other threading models when executing together. So for more information, you can look at our repo, contact us. There's documentation. All the documentation is available and updated regularly, like as part of CI in GitHub pages. Look at for events and information at UXL Foundation. I'd suggest the new book, since it's about oneTBB and the revamped TBB, but you can read one of our books to gain more information there as well. And then that really concludes my presentation. I just want to conclude by thanking everybody who's attending this talk, but also just to thank everyone who's been part of TBB's story over the years and continues to be part of the TBB story and the oneTBB story. It's really been, I'm sure there's been probably hundreds of people involved in making TBB what it is today. So thank you all. And do I have a few minutes for questions or?
Thank you very much. It was an amazing talk, and thank you to all of you. I mean, there are many developers here, so I think no, the future-proof design is shown to be really future-proof. Okay,
Yeah, 20 years
so
later,
perhaps
right?
it's, I mean, absolutely. Perhaps it's better we leave question at the end because we give also space to the users, no? So
Yes.
if Kylie, maybe you can also drop your question in the chat, and at the end we go over the questions. Can also work. Meanwhile, I ask Kylie to prepare to share to share the slides.
Yeah, I can do that. Let me.
Maybe Mike, you have to remove your slides from sharing.
How do I do that? I don't use, oh, let's see. Okay. I rarely use Zoom. I think, Kyle, you can just claim host.
Hmm. Share settings. Unfortunately, I don't see a way to do that.
Okay, I can stop. Maybe
All
you can,
right.
okay.
That should work
Right
now.
now, here we go. Very good.
Okay. Thank you for the chance to talk with you, and it's hard to follow Mike, to be honest. But uh, I'd like to share some of what we've learned and what we've done in the high energy physics community and talk about our use of oneTBB. So I'm presenting on behalf of myself and Mark Paterno. And also I'd like to acknowledge the other members of our team. Our framework that we support is called the Phlex framework. And I know at least one other of our developers is on the line, Chris Green. So yeah, let me tell you a little bit about what we've been doing with TBB. Most of us are from Fermilab, and Fermilab is about 35, 40 miles west of Chicago. And you see the big accelerator rings here. Now, the Department of Energy describes Fermilab as America's particle physics and accelerator laboratory. So let me talk very briefly about what particle physics is about. What we're after is trying to explore nature at its most fundamental level, and that tends to be at the most fundamental level, we're talking about particles. So there are various kinds of particles. You have quarks and leptons, which makes up matter, the stuff that we know and feel with our hands. And then you have things like forces, electromagnetic force, for example, that is carried by other kinds of particles. And one example would be a photon. There's another kind of particle that ties almost all of it together, and that's called the Higgs boson, which was discovered a little over 10 years ago. But how that all fits together is the realm of particle physics. And to actually explore those particles, we have to accelerate bigger particles like protons to very high energies. So that's why particle physics is sometimes referred to as high energy physics. So what we are doing at Fermilab is supporting the data processing needs of the DUNE experiment and probably later experiments coming down the road. The DUNE experiment is big. We create particles, and specifically, we create particles called neutrinos at Fermilab in Illinois, and then we send them through the Earth all the way to a mine in South Dakota. And at both Fermilab and South Dakota, there are very large machines or detectors that are responsible for detecting the signatures that occur whenever there is a particle interaction that comes from neutrinos. So our role as the Flex team is to find a way to efficiently help support the processing of all the signals that are coming from these detectors. So how do we do that? Well, the physics process itself within the detector, the one both at Illinois and the one in South Dakota, it creates data that is recorded. And from that data, we now need to infer what actually happened. And that's called the process of reconstructing. We're reconstructing the physics. And that's a complicated process. Particle physics is in the realm of quantum mechanics. Quantum mechanics is probabilistic and statistical by nature, so we have to record a ton of statistically independent observations. Once you do that, then you have to account for a whole bunch of other things to try to figure out the physics, like how well do you actually understand your detector? How well do you understand the environmental conditions? All these types of things need to be taken into account. Once you do that, you marshal all of the data at the right points, and you can actually identify the physics interactions and make some meaningful conclusions from them. You have to do that for all the data, a ton of statistical events, filter out what I'm colloquially referring to as the junk, and then analyze what's left and publish the results. So I can fit it all on one page, more or less describing what happens, but it's a complicated process. So how do you do that? Here is an example of a simple workflow, simple in quotes, that is actually used by the DUNE experiment. What are all these little nodes here? It's clearly a graph, but the elliptical nodes represent the algorithms that we don't actually define. The Phlex team, the Phlex framework developers, we don't define the algorithms at all. It's the physicists who define the algorithms. And it may be many different physicists with many different algorithms needing to piece them all together in a way that makes sense. It is the responsibility of the Phlex framework to make sure how they've requested things to fit together can actually work, and that workflow can operate in an efficient manner. So you have these elliptical nodes representing algorithms, and then it's the data that are passed between the algorithms, which are represented as these boxes. So it's a very busy slide as it is. Unfortunately, it's much more complicated than what you actually see because there's a lot of hidden dependencies. So we have to figure out a way to be able to process these types of things. And it's not just this one workflow. There are many different kinds of workflows depending on the use case. So how do we go about using computing resources to go about achieving physics results? Well, multi-threading is a very reasonable way of doing this. And in fact, the first explorations that I could find on the archive were back in the early 2000s, where they were looking at using threads to do parallel processing. So that was the meaningful abstraction at the time. About 10 years later, and Mike already referred to the release of TBB, which was before 2014, but it was around 2014 where the first high energy physics experiment, CMS, used had its own reconstruction framework. It was that framework at that time that used TBB to start expressing things as tasks. So we're no longer thinking in terms of threads, but the abstraction has moved to tasks. And many experiments and projects within high energy physics followed suit and started using TBB. And Mike already referred to another effort that was dealing with particle transport. It was from CERN around that time. So the previous workflow that you saw on an earlier slide uses the ART framework, and that also relies on tasks. But as you saw, that workflow is clearly a graph. So if we could find a way to think in terms of graph, we should do it. And that's when in about 2024, we started exploring, can we move from TBB tasking specifically into a flow graph based paradigm. So that was called MELD in 2024. So the argument is that flow graph is ideally poised for handling HEP data processing. The difficulty in high energy physics is that most of the existing software out there thinks in terms of stateful objects, where there's not a lot of careful concern for what things are mutable and how do you achieve safe and efficient concurrent processing. So I already told you about MELD, but starting at 2025, we started putting together the production framework that is called Phlex, and that's what my team and I have been working on for a couple of years. So starting in early 2024, we started to have conversations with Intel, Mike, and the other oneTBB developers of how can we best leverage oneTBB to achieve what needs to be done for DUNE and high energy physics in general. So we had our first meeting back in February of 2024. We had a subsequent meeting where we had some follow-up from the oneTBB developers, Konstantin in this case, presenting a slide on a feature that we required. And we've had many meetings since that time, and here's just a screenshot of us meeting all together, talking about some of the finer points of TBB and what was coming out at that time. It's been a very fruitful collaboration. One of the things we were encouraged to do was to create an RFC for one feature that we required, which is limited resources. Sometimes, actually, often in our field, you will have algorithms or nodes that need to access a thread unsafe software, and it's not sufficient to say that one node in the flow graph can have a maximum concurrency of one. There has to be a coordinated access to a thread unsafe resource to make sure you don't have data races. So that preview feature was released for oneTBB 2023. Many thanks to Mike and team for putting that together, and we've been trying to include it in the framework now. There's another RFC in the works having to do with folds, and I'll talk about those more if folks are interested. So oneTBB flow graph is well suited to meet the data processing needs of the DUNE experiment and HEP in general. We've had incredibly productive interactions with the oneTBB developers. We use TBB better than we did, and it's led to some feature enhancements in oneTBB itself. So thank you for your time and for the opportunity to present to you.
Thank you very much.
Yep.
So if you have questions, please write on the chat. So we make this way we save some time. And meanwhile, I introduce you Federico Ficarelli from CINECA. I invite him because I know CINECA is undergoing a huge, massive porting of CPU code to oneTBB, and he is going to present one of this work. Please, Federico.
Yep. Hi, everyone. Let me see if the screen sharing gods are on my side now. Nope. Let me see. Okay, I'm sorry, I have to close Zoom and reopen because macOS is not like happy about me fiddling with security settings. Gonna be back like in 2 seconds.
Okay, so perhaps meanwhile, maybe now we can use this 1 minute to answer the question. If you have any question regarding the talk we already have by Michael or Kylie, please go ahead. I think what is very interesting is also the call for action. So by Mike, we have this is an open source project, open governance. So there is a way, there are channels to communicate and to contribute to the project. And as you have seen from Kylie presentation, it's relatively easy to get involved in the project and to contribute. Okay, here we go. Now we see your screen, Federico.
Okay, nice. Sorry for that.
Maybe put full screen. Okay, very good.
Okay, thanks. Sorry. Hi, everyone. I'm Federico Ficarelli. I'm from CINECA, that is the Italian National HPC Lab. And today we're going to see one of the, actually the latest use case in which we use TBB very fruitfully. So we are very happy about that. But this use case is part of a larger effort that started quite some time ago, like in the early 2000s. So at CINECA, we mainly design, deploy, and operate top 500 machines. But we also do a lot of like research work, both in academia and with companies. So in this case, we're talking about the work we're doing in my team with pharma companies, especially with DUNE pharmaceuticals. And the whole thing is the whole goal of the effort is to unlock HPC or essentially hybrid large-scale computing resources to pharma scientists. And the overall use case we are looking at today is called virtual screening. So essentially, it's the process of ranking a large set of potential drugs against viral proteins to move ahead those who are likely to be potential drugs towards more and more expensive stages of testing, like wet labs and actual compound synthesization and stuff like that. So this is the overall overview. Of course, when we have to deal with billions or even trillions of potential drugs, aka molecules, like small molecules usually, we cannot rely on very precise methods, aka we cannot involve quantum mechanics, for example. So everything is designed with domain scientists to strike a balance between overall throughput, and the precision of results. So just a quick note about the actual usage of the platform we have been working on for the past 20 years. Just to say that, just to remark the fact that everything we're going to see is currently in production. And one example is from the pandemic's time, when the European Union launched this project called Escalate for COVID, where called for HPC to help in fighting the pandemics. So the consortium was pretty big, so we were able to go up to clinical trials through actual compound synthesis. But our task was to screen what was and what is still, I think, the largest virtual screening library ever attempted. So we managed to reserve the two largest machines in Europe back in the day and use those for 3 days straight to perform experiments. So we were able to scale to pretty large, like HPC resources. From the overall workflow, virtual screening workflow, today we're going to see like the latest use case that is called conformal generation. And in a few words, the task is to take a-dimensional representation of potential drugs that are represented as linearized graphs without any kind of 3D configurations. So they're just like topologies, chemical topologies. And the goal is to run a bunch of combinatorial chemical reactions to produce an even larger data set, and then produce like feasible 3D atomic structures without using very expensive methods like molecular dynamics or quantum mechanics. So we essentially rely on state-of-the-art methods, so mainly on force fields and gradient-based methods for relaxation. So the workload is a weird mix of graph processing, graph mutation, linear algebra, and numerical methods. And the most computationally intensive part, that is the actual energy minimization, has been accelerated via SQL kernels, via warp synchronous SQL kernels. We're going to see what does it mean. And we recently presented this work at iWalk this year. And the one very nice thing is the fact that we expose all the chemical features of the library as APIs. But alongside APIs, we provide also TBB flow graph nodes. so the user can compose their own workflow. So this is a very simplified example of a quite common processing graph. We use quite a large number of features from TBB flow graphs. For example, we have like input nodes with limiter nodes to provide back pressure. We are currently experimenting with token-based systems, but right now we deployed limiter nodes. We use, for example, pairs of broken nodes and join nodes with key matching to allow the user to compose straight line pipelines with respect to the functionalities that they need. For example, here we have like on the top pipeline is the actual conformer generation pipeline. That is like a straight line of multifunction nodes that perform several like chemical tasks. And then we have a sync node to perform the actual minimization. But moreover, the user added like another pipeline to compute several embeddings for later AI models to consume. And so essentially, we keep those pipelines synchronized via join nodes with key matching. And one detail about the async task, so how we manage GPU offloading. So the nice thing about having a heavily task-based workload is the fact that parallelizing on CPU is pretty easy because every task, aka every molecule, is a thing on its own. So it's very easy. The problem comes when you have to keep GPUs busy. So we somehow need to coalesce tasks in batches to keep GPUs busy, essentially. And the first implementation that we tried of this technique called dynamic batching that we borrow from NVIDIA Triton inference server was implemented directly in TBB flow graph nodes. But then we realized that it was too complex. So we opened the hatch by using the sync node. That was really nice because it allowed us to implement the dynamic batching logic in pure C++ with pure parallel C++ with OS threads that are meant to be idling as much as possible. So they're just pure IO threads. While on the TBB task arena side, we just have to perform the async node protocol and push task on an npmc task queue, and everything works pretty nice. Dynamic batching is like it's a nice way to strike a balance between latency and device occupancy because via parameter tuning for a specific system, we find the best parameters both for the delay. So for how long are we allowed to wait for a batch to fill up, and the actual size of the batch that mostly depends on the GPUs that you have on the system. So the dynamic batching allow us to strike a balance between those two parameters. So we usually run parameter search on the system, and then we have the two optimal parameters that we use statically throughout the simulation, actually. And yeah, just a quick note on the performances. This is something that we presented earlier this year at iWocal. Both on GPU accelerated systems that are based on x86 and with NVIDIA hardware. So we actually deployed SQL kernels on NVIDIA hardware, on NVIDIA 100s, on the Leonardo supercomputer. But we also benchmarked CPU-only systems, so without GPUs, just pure TBB, both on x86 and ARM systems, especially on NVIDIA Grace superchip systems. And apart from the actual speed up in terms of throughput, that was pretty nice versus the actual state of the art. I think that the most nice plots for TBB's sake are multi-core scale out performances. So actual strong scaling on a CPU only node. On the left, you're going to see the Grace superchip system provided by the UPEX project with more than 140 Neoverse cores. And as you can see, the scale out is amazing. So it's like almost theoretical. And the scale out comes from pure TBB. So the chemical library itself is a scalar. So we don't use any kind of parallelism programming model. It's just pure C++. apart from BLAS and LAPAC parts, but that's another story. On the right, you see an x86 system, aka the Leonardo supercomputer, where we have a pretty bad thermal throttling at around like 44 threads. But up to 44 threads, you see that the scaling is actually theoretical, right? And the very nice thing is the fact that we can add functionalities as oneTBB graph nodes, and then provide the user with the possibility to design a graph, aka an experiment that scales out pretty well. So we are very happy about it. And I'm done. So thanks everyone, and thanks also all the TBB community. And I actually have a first edition of the TBB book floating around, and that's it. Thanks.
Very good, very good. Thank you very much. Thank you very much. It's also nice to see different system working with oneTBB, which also is one more proof that is a very good design, in my opinion. So we ran a little bit late, but maybe we can, if any of you has a question. I mean, the true goal of this meeting is to, to make connection more than, more than anything else. So it's clearly sometimes technical discussion needs to be happening in other places. But I'm very happy to have seen we reached the 33 participants. Plus, there are many people who I know that will watch the video later. Um, if there are no questions, no, are there any questions? If no, I want to thank all of you, all the oneTBB developer, to Mike, Kylie, and Federico for the presentation. It was very amazing, and thanks to Mike also for helping the organization, helping finding the speaker and all of that. So with this, we conclude this meeting, and I will let you know the agenda for the next meeting, which likely the team will be back to SQL. Thank you very much, and see you soon.